Hi, physics class. This is your video lecture for Monday, January 11th. When looking at the quiz results from Friday, realized I needed to spend a little bit more time with you on solving problems based on Newton's second law, using free body diagrams, and how to put these things all together. So today is kind of a quick review over some of the key steps. Hopefully this will help put some things in perspective. The first thing I want to talk about are free body diagrams. Free body diagrams. They have their sole purpose is to help you identify all forces involved and their direction of those forces. Right, that's all a free body diagram is meant to be. So let's start off with just an example. Whoop, I don't want to do a circle, let's do a square. Let's just start off with a box. And let's forget a moment. Let's just think this box is falling. It was dropped out of an airplane. This box is falling. And let's ignore air resistance right now. Let's ignore air resistance. So if we've got this box and it's falling, what are the forces acting on our box? Well, hopefully you're going to say, well, yep, there's a force. Whoop, let's do an arrow. Hopefully you're going to say, yep, there's a force going down. And what force would that be? That would be the force due to gravity. That would be the force due to gravity. So let's label our force over here. And in this case, since I asked you to ignore air resistance, there's no other forces acting on our box. So a box that's freely falling, very simple free body diagram. Now, we could take this whole idea a step further. Whoop. Let's take our box again. And let's say that it's falling, but this time let's not ignore the air resistance. Let's not ignore air resistance. And so let's put everything in here. So again, we still have gravity acting on our box. So let's put in our force due to gravity. But if we have air resistance, how do we draw air resistance in? Well, first I want you to think about what direction is air resistance going? Air resistance is always going to oppose your motion. Right? So if we were going on a horizontal surface, we're driving a car, air resistance is going to go against our direction of motion. And the same thing happens when something's falling through the air. Air resistance goes against its direction of motion. So we know that our direction of motion, our box is falling, so we better put our arrow up for our air resistance. And let's go ahead and label that F air. So our free body diagram got a little more complicated. We have two forces here. All right. So here's the beginning of what we want our free body diagrams to tell us. What we ultimately want to get to is to understand the net force acting on our object. So if we look over here, I'm going to type F net equals, we should be able to read it right off of our free body diagram. Well, if we look at our free body diagram, in the case of the box falling with no air resistance, there's only one force, and it's gravity. Now, what I want you to think about here a moment, in our box, we drew gravity with an arrow pointing down. That's the negative direction. The negative direction. So when we write what our net force is, we're going to put a negative in front of our F gravity because it's in the negative direction. Okay. That's important. If we take our negative, if we pay attention to our directions when we draw a free body diagram, that helps us figure out what signs to put in when we write our equation for our net force. And that keeps everything nice and orderly for us till we get to the end, and we don't have to worry about negative signs or anything like that. If we do it right up front, draw our arrow here with the correct direction, write it down in our F net with the correct sign, negative being down, our signs are going to work well for the entire problem. They'll help us out in the end. Well, what would the net force equation look like for a box falling with air resistance? Well, it's going to, hopefully you can look at it. It's going to start off the similar. Well, let me get the copy this over. It's going to start similar, right? Because we still have a force of gravity pointing down. But what's different here? What's different here? Oop, I got to make this so it fits a little bit better. This one has a force due to air resistance. Now, what direction is that force facing? It's positive. It's going up. So here we write our equation for our net force. Our air resistance force is going to be positive. See how the signs just automatically fall out? You draw your arrow, draw them in the right direction on your free body diagram. Then when you go to write your net force equation, if the arrow is pointing in the negative direction, put a minus sign. If the arrow is pointing in a positive direction, put a plus sign. Okay? And these could get more and more complicated. Let's do another example. Let's do one more with a box. How about the box just sitting on a table? How about a box just sitting on a table? Well, here, again, we're still going to have gravity working on our box. Hopefully that makes sense. Not out in space where there is no gravity. But we also know that the box, when it's sitting on the ground, it's not accelerating into the ground. So we know there must be some other force there because we don't see it accelerating into the ground. What I want you to remember here is we called that a normal force. The ground is exerting a force back up on the object. And we called that a normal force. Why do we call it normal? Because it is normal to the surface. Normal to the surface meaning it's perpendicular to the surface. Perpendicular to the surface. Right? So if our box is just sitting on the ground, right? Let me put some descriptions above these. So let's go up here. What do we have here? Free falling box. What does that mean? No air resistance. Here we have a box falling with air resistance. And what do we have over here? This last one's going to be a box sitting on the floor. Okay. Let's draw our F net. Let's come up with our F net for this last one here. What's our F net? Again, when we look at our equation, we've got gravity pointing down. Since our gravity is pointing down here, we have to put a negative sign in it. We have our F normal pointing up. So let's go ahead and put that F normal in. And F normal. Right? Pointing up, we have a positive sign. Let me do one more here to get a little bit more level of complication, and we're going to move on to our next part. What if we did instead had the box, now said our box was on a slope? With friction. Okay. Our box is on a slope with friction. So let's see if I can get here's our slope. Let's put a little box on our slope. There we go. So let's draw our free body diagram force for this. Again, we're on the surface of the Earth here, right? So we're going to have gravity. Which direction does gravity point? Gravity always points straight down. Always points straight down. It will never point at an angle. It's always pointed to the center of the Earth. So we've got our force due to gravity. How about our normal force here? Right, our box is not falling down into the ramp. It's falling down along the surface of the ramp, but it's not falling into the ramp. So there must be some force that's preventing it from falling into the ramp. So we got to go ahead and draw that force. Now this is a normal force. What does that mean? It's normal. It's perpendicular to the surface. Perpendicular to the surface. Okay. Now we also have the force of friction. We also have the force of friction. Now friction opposes the direction of motion. Right? And we have two types of friction. We'll learn about that here soon. But we have something called static friction. So when it's not moving, this is the friction that keeps it from moving. And we have dynamic friction, which is when it's already moving. All right, so whether our box is moving or not, let's just assume the box is moving. What direction do you think friction would be? Well, hopefully you'd be sitting there thinking, wow, well, if the box is moving, it's going to be moving down the hill. Let's put our frictional force going up the hill. Let's put our frictional force going up the hill. So let's bring this guy, let's label him down here, and let's put a little F for friction. Okay. Now, even if it's not moving, you know that if there was no friction, it'd be trying to slide down the ramp. So if there's friction, if it's not moving, that must mean there's a friction force holding it from falling down the ramp. That friction force is still pointed up along our ramp's surface. And there's the free body diagram. Right? We identified the three forces. One of the things I saw in the quiz, though, that I want to highlight here, because I don't want you doing this. This would not be correct. Do not draw a force like this. There's no force pulling our object down the ramp. We do have a net force. This is true. And that net force is what's pulling it down the ramp. But that's combining the other forces that already exist to come up with that net force. There's not something else magically pulling on our block other than friction, gravity, and the normal force. So I don't want you putting in an arrow here like I have a red one, because just because it's moving down the ramp doesn't mean there's another force there. What force would it be? Unless you're pulling it with a string or pushing it down the slope. There's not another force involved here, so be careful. Don't do that. Okay, don't do that. There's not a force there. All right, let's talk about the other part here before we do a couple problems. And the next thing I want to talk about is Newton's second law. What is Newton's second law? F net is equal to ma. I'm going to be very specific saying that, and I'm going to try to do my best to always write this as F net equals ma, because that's really what Newton's law is telling us. Newton's law said if there's an unbalanced force, so the F net is not equal to 0, right? If there's an unbalanced force, F net's not equal to 0, then there's going to be an acceleration. You have to have an unbalanced force to have an acceleration. Object in motion tends to stay in motion. Object at rest tends to stay at rest unless acted upon by an outside force. Right, that was our law of inertia. That was our first law. And this is how it gets embodied in the second law of motion, F equals ma. And again, I want to be very careful. This is F net. This is the sum of all of our forces. The net sum of all of our forces will determine the acceleration of our object. I also want you to see that both our force and, I thought I did that. Let's go back and fix that there. I also want you to see that the force and the acceleration, right? Force and acceleration, they have to have the same sign. What does that mean? That means they're in the same direction. So if our force is in the negative direction, if our net force is in the negative direction, our acceleration is going to be in the negative direction. If our acceleration is in the negative direction, our net force must be in the negative direction. Right? I also want you to see that if the acceleration equals 0, then F net equals 0, and vice versa. Right? If the net force is equal to 0, acceleration is equal to 0. Okay. Okay. And this is all Newton's second law really tells us. If there is a force, if there's a net force, there's an acceleration in that direction. If there's an acceleration in a certain direction, that must mean that there is a net force in that direction. That is all Newton's second law tells us. Now, I do want to be a little careful here, because oftentimes we use a generic equation, F equals ma. And then we can use that a lot. That's a good definition of it. But when we're talking about Newton's second law, it is the net force that we're talking about. Right, so sometimes I might talk to you about the force due to gravity. What's the force due to gravity? M, just like we have in our Newton's second law, and G, that's the acceleration due to gravity. This is not the same. The form looks very similar. Force of gravity equals mass times gravity. Very similar to a form that we have here in Newton's second law, the net force equals mass times acceleration. But they're very different. Right? Our force of gravity is always going to be in the direction of gravity. Doesn't tell us anything about the acceleration of the object. All this tells us is what's the force due to gravity. Right, we have to use our free body diagram to figure out what the acceleration of our object is. All right, so let's put these all together. Let's put these all together. So we did, let me go back to that first slide here. And on each of our 4 pictures here, I didn't put an F net here on the bottom one. We'll do an F net with this kind of a structure later on. This is a very complicated one, and I don't want to belabor the point here. So the box and the slope with friction gets a little bit more complicated. We'll do those a little bit later. We'll do those next, actually, in the next part here. But let's see what our acceleration here is. Right, so if we look at our first one here, what does Newton's second law tells us? F net equals ma. So in this case, what's our acceleration? Negative Fg equals ma. Right. Negative Fg equals ma. Very, very simple here from our free body equation. But we also know just from the definition of a force of gravity, get this in here. Definition of a force of gravity is mg. So if we look at this equation, and I would try to combine these two, Fg is equal to mg, so that gives us negative mg equals ma. Cancel out the m's on both sides. What do we get? Negative g equals acceleration. So our acceleration's in the negative direction, and the magnitude of g, negative 10 meters per second squared. Well, that makes sense just by looking at it. There's no other forces. So I can write underneath here, negative mg equals ma, which then tells us what? Negative g equals a. Gravitation, force of gravity is the only one here, then it makes it real simple. Let's look at how this would apply to our box falling through the air with air resistance. And what I want you to see here is whether it's falling with air resistance or whether it's sitting on the floor, our free body diagram looks amazingly the same. All we did is we changed our little suffixes here. The first up here was force air, up here it was force normal, but the structure is still the same. Okay, structure is still going to be the same. Let's use Newton's second law on the middle one. Well, we know Fg minus F air. We also know from Newton's second law, F net equal to ma. So we can plug in for both sides here. What do we get? Negative Fg plus F air equals ma. And all I was doing was putting those two equations together. Right? The one we got from our free body diagram and the one we got from Newton gives us this equation. Okay. Now, if we're told that our box is falling through the air and it's at a constant speed, what does it tell us? It tells us that our acceleration would be 0. It tells us acceleration would be 0 here. Well, if that means the right-hand 0, what is that? Right-hand side 0, what does it tell you about the left-hand side? It tells you that the negative force of gravity plus the force of air resistance equals 0. Or in other words, force of air resistance is equal to the force of gravity. Hope that makes sense. They're equal and opposite forces. They're canceling each other out. There's no acceleration. But what if there is an acceleration? Well, typically, if you don't hope you from your experience, you throw a box or a rock out the window of an airplane, it's going to fall down. Right? Air resistance isn't going to be enough to overcome the force of gravity until the object reaches terminal velocity, and then it'll equal out. But we could solve several different equations, several different scenarios, just by combining our free body diagram with our Newton's second law. And those equations are all going to be driven by this one then, the combination of them. So we might have if the object is still accelerating because our air resistance isn't strong enough, that tells us we're going to have a negative acceleration, right? That tells us again our F air must be smaller than our Fg. At some point, your air resistance is going to be equal to Fg, which tells you your ma equals 0. If your acceleration is 0, you're not accelerating, you're at a constant velocity. That puts several of these things together. Let's do one where it's a little bit more complicated. I want to do an example here of an elevator. So let's say we have an elevator. And let's put our free body diagram in here. Right, we have gravity going down. We have some sort of a cable pulling up. Let's put in our labels for this. FC, let's call FC our cable force or our tension force in our cable. Let's label here, FG. All right. So what if our problem tells us a couple things? Let's try this as a starting point. Let's say that our mass of our elevator is 1,000 kilograms. Let's see, we know that the acceleration due to gravity is 10 meters per second squared down. And what if this problem further told us one more piece of information? What if this problem told us that our acceleration was negative 2 meters per second squared? And then finally, it's asking us, what is the tension What is the tension in the cable? Or what's FC? So we need to do our problem here in two parts, right? We're going to do our problem here in two parts. Let me draw a line here to kind of separate out what we're doing. And the first part I want to do over here is Newton's second law, or is from right straight from our free body diagram. We're going to use our free body diagram to find the net force. And we can write this out. F net equals what? Looking at our diagram, what do we see? We have FC pointing up, so we're going to have a positive. We have FG pointing down, so we're going to subtract it. Okay. Well, the problem also told us the mass of our elevator was 1,000 kilograms. So we can plug that in. Let's go ahead and plug that in. So F net is equal to FC. Well, we have mass is 1,000 kilograms. Gravity is 10. So let's plug those in. What do we get for our answer? We're going to get F net. Go to FC minus 10,000 newtons. Okay. So we still can't find the tension in our cable FC because we don't know what F net is. But we do. And then we need our help from Newton's second law to tell us this. Newton's second law tells us F net is equal to MA. F net is equal to MA. Well, let's go ahead and let's plug some things in because our problem told us that our mass was 1,000 kilograms. It told us that our acceleration was -2 meters per second squared. If we plug all that in, what does it tell us that our F net is equal to? 2,000, -2,000 newtons. Now again, I want to be careful. That negative sign is important because our acceleration was in a negative direction. We got to make sure we keep that in there. And that tells us that our net force is also in the negative direction, -2,000 newtons. Well, let's go ahead and plug that 2,000 newtons in for our net force, and we can plug it into what we found over here on the left to figure out what our FC is, our tensional force is in our cable. So we can replace F net let's see, let me just do this. I can just copy this little piece here. So let's plug in things. We just figured out that our F net was equal to -2,000. So I'm going to write in -2,000 newtons is equal to FC minus 10,000 newtons. So what is our FC equal to? That's pretty easy to see. FC equals 12, and sorry, -2 plus 8 is going to be 8,000 newtons. Okay. Let's look at our answer here for a moment. FC is positive. Does that make sense? Sure does, because our cable was pulling our elevator up. Right? Our cable can't push our elevator down. So the only direction our force for our cable can be is in a positive direction. So our answer here for our force due to our cable better be positive, and it is. Good. We also see that our force to our cable is 8,000. Well, let's just do a quick reality check. if we've got a force of 8,000 pulling up, and we calculated our gravity over here being 10,000 pulling down, what's our net force going to be? Our net force is going to be negative. Perfect. That's what we saw over here when we were dealing with Newton's second law. We figured out our net force was negative. You want to do that quick comparison. Does your number make sense? Right? We could have done a math error in numerous ways to come up with an answer that doesn't make sense. One of them being if we came up with a negative number here for our tensional force or FC, that would be a problem. We know we've done a mistake someplace. Go back and look. If we ended up here with a number that was, say, 15,000 newtons, then we're going to go back to our diagram, look at it. We've got a force of 15,000 newtons up. Gravity was only pulling down with a force of 10,000. That means we have a net force up. Our acceleration should be positive. Well, we know from our problem our acceleration must be negative. So we've done something wrong if we come up with our FC being bigger than our FG. Okay, quick gut check on that. All right, I want to do the same thing here, but let's tweak this problem. Let's tweak this problem. And instead of giving you the acceleration, I want to give you the tension force in the cable. Let's say that tension force in the cable is 4,000 newtons. And again, notice I've got the tensional force in the cable FC. It's positive, which makes sense. That's what it is from our diagram. It should be positive. Well, if we know our tension in our cable, then the question here is going to be, what is the acceleration? How does that change our problem? We're still going to use, from our free body diagram over here in step one, it's still going to be the same. We still have F net is equal to FC minus FG. Awesome. Now, we don't know, we do know our FG here because we do know our 1,000 kilograms. We know that gravity is pulling down with 10 meters per second squared. So we still know the second piece here. And instead of on this third piece, now we plug in all the numbers. What are we going to get here? Let me just delete. I don't want to delete this one yet. We plugged in our values for mass and gravity. Let's plug in our value here for our force due to the cable, and it told us that was 4,000. So what's our net force here? F net is going to be equal to negative 6,000 newtons. Okay, we have enough information, we can calculate the net force. Well, let's go over here and let's look at the second side. Let's look at our Newton's second law part. F net equals ma. Well, we don't know what ma is. Right? We know what mass is, but we don't know what our acceleration is. So I'm just going to put an a here and leave it at that. But we just figured out what F net was from the left side of our calculation here. Right? We found out that F net was negative 6,000 newtons. So let's plug that in over here. Negative 6,000 newtons equals 1,000 kilograms divided by A. Let's divide both sides by 1,000 kilograms. And what are we going to be left with? Negative 6 newtons divided by kilograms. We're looking for acceleration. So you guys know by now, acceleration has units of meters per second squared. We just found our acceleration. Well, hoping that makes some sense here. So we just did two different free body diagrams, two different scenarios. Let's do one more. Notice our acceleration, before I go there, our acceleration was negative. Does that make sense? Yep, our force up was 4,000. Our force down from gravity was 10,000. Yep, we have a net force down. We better have an acceleration down or negative. Let's do that same problem, but I'm going to tweak things. I'm going to change this to be Let's make this 16. Make it 15,000 newtons. So our force, our cable is 15,000 newtons. We can go through this whole same calculation. All we got to do is replace it with 15,000 where we had our 4,000 before. So I replaced it here. That gives us a net force of what? Positive 5,000 newtons. So we go and plug it in to the right now that we've redone our calculation based on the new values in our free body diagram. Over here, instead of -6, we have 5,000 newtons. 5,000 newtons divided by 1,000 kilograms is going to give us what? 5 meters per second squared equals our acceleration. Now, what I want you to see here again, let's take a quick gut check. Our acceleration is positive. Does that make sense? Let's look back at our free body diagram. Yep, we've got a force of gravity of 10,000 newtons down. We've got a force on our cable of 15,000 newtons up. Our net force is up. Our acceleration better be in the upwards direction or positive as well. Okay. I want you to do that quick gut check at the end. Make sure your number makes sense. That's all I wanted to cover for today, guys. Hopefully this helps in understanding free body diagrams, Newton's second law a little bit, how we put all these things together to do some Newton's second law calculations of our motion. All right. We'll talk to you tomorrow, guys. Have a good one. Bye-bye.